Okay, let's talk about CNN architectures. These are the components of CNNs, convolution layers. We talked about it, and we also talked about pooling layers. Where did you use pooling layers? Sometimes the input images are too large, like 1024 by 1024. In this case, we need to handle big feature maps, and that is costly computationally. In those cases, we want to reduce the number of channels, not channels, but number of width and height. In such cases, we can employ pooling layers. And to reduce the number of channels, we can use one-by-one convolution, and we can reduce the number of channels, and we can achieve computational efficiency. And we also talked about fully connected layers. This was basically used for linear classifiers. However, after a series of convolution layers, feature maps become manageable like this. And at the end, we connect fully connected layers and we receive or output the score functions, scores for each classes. And we talked about activation functions, and we used the same activation functions as in general linear classifiers. And we also talked about normalizations like batch normalization, instance normalization, and group normalization. We can use those components also for CNNs. And using these components, how can we design the architecture of CNNs? That is the topic of this video. Okay, before then, let's recap what batch normalization was. In this case, the input was n by d shape, and we calculate the mean and variance and normalize the values. And we can insert batch normalization into various locations. And usually batch normalization comes before nonlinear activation. And sometimes we do not want, the network might not work best with zero mean and unit variance. To handle this case, we employ extra parameters, gamma and beta, so that the distribution might be different from zero mean and standard unit variance. And during test time, we cannot calculate the values for mean and variance because during test time, we only handle sometimes one sample. In this case, calculating the mean or variance is meaningful. Therefore, we're going to use running average of values seen during training or running average during testing. Anything is okay. And during testing, batch norm becomes a linear operator, and we can fuse batch norm with previous fully connected layers or convolutional neuron convolution layer. All right, and how do you use batch normalization for ConvNets? In the case of fully connected layers, the input shape was n by d. However, for images, the shape is n by c by h by w. In this case, we normalize the instance dimension as in fully connected layers. This is the instance dimension. And we calculate the mean and variance through this dimension, and we do the same for images. And this is sometimes called spatial batch norm or batch norm 2D. And we take the mean and variance through height and width dimensions as well. So you need to be careful when you're calculating mean and variance and gamma and beta. And there is another normalization technique called layer normalization. In the case of batch normalization, we take mean and variance through the instance dimension. On the other hand, layer normalization takes mean and variance through this data dimension. So it calculates mean and variance for each data. And we can do the same for instance normalization. We can extend basic layer normalization into instance normalization. We take normalization through these H and W dimensions. Okay, so in contrast to batch normalization, which calculates the mean and variance through 3 dimensions, instance normalization calculates mean and variance through H and W dimensions. So these are the differences. And we saw on this picture, we compare each normalization pictorially. And group normalization generalizes these normalization techniques. Okay, that was a short recap of normalization layer. And the question we're going to talk about from now on is how are we going to combine these components to make or design an architecture for our CNN? And to do so, what we are going to do is we're going to have a look at previous CNN architectures. And from these previous CNN architectures, we can get some ideas how we should design our CNN architectures. Because these architectures did not just come out suddenly out of nothing. However, this architecture was built on the previous architecture, this one as well, built on top of these 2 architectures. And this architecture also motivated, inspired by previous architectures. Therefore, what we are going to do is case studies, how these architectures were designed and how each architecture affected other architectures. And by looking at the motivation of each architecture, we can get some ideas in the motivation and the design techniques. And by learning from these architectures, we can design our new architecture based on these previous architectures. Okay. And CNN architectures were designed based on the ImageNet challenge. I introduced this challenge before. This was very foundational computer vision challenge. And people wanted to solve this problem as a CV researcher. And performance, this is the error bar. Performance was not that satisfactory in the early 2010. The human performance, the error rate, is about 5.1. However, in 2010, even the best model showed the error rate of 28.2. So that was far below than the human performance. However, after 2015, deep models became superior to human recognition system. And in 2012, before 2012, the improvement over the year was less than 5 points, like around 3 points. However, in 2012, there was quantum jump, like around 10%. And this was the first CNN-based winner. And another milestone is 2015. After 2015, the performance of CNNs became better than, superior to that of human. Okay, so there are two milestones, 2012 and 2015. Okay, we're going to have a look at the very first CNN architecture that revolutionized the ImageNet competition. The architecture is somewhat simple. It contains 8 layers. The first layer is conv layer, followed by max pooling, normalization layer, and next convolution, followed by another max pooling and normalization, and 3 consecutive convolution layers, and another max pooling, and 3 fully connected layers. Compared to modern CNN architectures, AlexNet is quite simple. And the input size was 227 by 227 by 3. Basically, the input size should be 224 and 224, but maybe the authors used padding to make this image size as 227 and 227. And the first layer consists of 97 11 by 11 filters, and the strut size was 4. And what is the output volume size? This is kind of a recap. Stop the video and think about it on your own, and let's check the answer together. All right, let's check the answer together. The output size is 55 by 55 by 96. Quite simple. So this was the height, width, and the depth was quite shallow. However, after the first convolution, it became deeper, and the width and height shrinked like this. And what is the total number of parameters in this layer? Also stop the video and think about it on your own, and let's check the answer together. All right, what is the total number of parameters in this layer? Because we have 96 filters, and the filter size is 11, and the depth is 3, because the input has depth of 3. And this one corresponds to a bias. It has around 35,000 parameters. Okay. And the second layer is 3 by 3 filter, max filter, pooling, applied as stride 2. And after this, the input size becomes, it was 55 by 55 by 96. The output size becomes 27 by 27, and the number of channels does not change. And what is the number of parameters in this layer? Because this is a max pooling layer, it does not contain any parameters. So the number of parameters is 0. Okay, and we can proceed up to the end of this architecture. And the input size was 227 by 227 by 3. And it becomes 55 by 55 by 96. And after max pooling and normalization, the dimension does not change like this. And after the second convolution layer, channel increases from 96 to 256. And there are 3 fully connected layers. And because ImageNet has 1,000 classes, it should output 1,000 class scores. That is why there is a fully connected layer with 1,000 units. Okay, the details and lessons from this design are these. This architecture first used the activation ReLU. and it used LRN layers for normalization. However, no one uses this layer anymore. And they applied heavy data augmentation, and they also used dropout. At the time, batch normalization was not designed. So rather than batch normalization, they used dropout. And they used the size of 128 as batch, and they used SGD with momentum for optimization. And learning rate was set as this, and they reduced the learning rate manually when the validation accuracy did not change, plateau. And they also used ensembles of 7 CNNs. And by using 7 CNNs as an ensemble, the accuracy improved like this. So what is ensemble? They train separate 7 CNNs. And each image goes through all these architectures, all this network. And these networks might say different answers. Like for the cat image, it might say cat, cat, dog, cat, dog, dog, cat. And by voting, we have 4 cats and 3 dogs. And the final results is going to be cat. Therefore, by using multiple models, the accuracy improves. Okay, and historically, they trained this model on GTX 580. Nowadays, we have A100, H100, this kind of huge and gigantic GPUs. And we have 8 GB as a memory. However, at the time, this GPU had only 3 GB of memory. And they used 2 GPUs and half the neurons on each GPU. So these layers were trained on the same GPU. And these layers communicated across 2 GPUs. At the time, there was no PyTorch or TensorFlow. So researchers needed to make programs for using GPUs, using the CUDA library. Therefore, it might be much more difficult to implement these ideas. However, this was the first very seminal work that demonstrated the validity of deep neural network for the first time in the area of computer vision. Okay, so 2012, AlexNet was the very first CNN that won the ImageNet challenge. And in 2013, this network called ZFNet came out and reduced the error rate from 16 to 11. However, the architectures were just the same, was just the same. However, they changed the parameters, hyperparameters, and found the best combinations for the performance. So rather than using 11 by 11 with stride 4 as the conv1, they changed it to 7 by 7 convolution with stride of 2. And they also changed the number of channels or the number of filters for convolution 3, 4, and 5. Instead of using 384 and 256 filters, they used these numbers and the top 5 rate reduced like this. Therefore, ZFnet was just re-implementation of AlexNet. However, they also demonstrated that different configurations would result in different performance. Okay, and after 2013, deeper networks start to come out. The first 2 deep neural networks, CNNs, were not that deep. They contained only 8 layers. However, in 2014, the winner started to have 19 layers or 22 layers. And that is called VGGNet. Even though this is an old model, still nowadays, some researchers use VGGNets. And the main idea was, rather than using big filters, use small filters. In doing so, they can make network deeper. And AlexNet could have only 8 layers. However, by applying small filter size, they could stack 16 to 19 layers. And the performance improved as well. And this is the architecture of VGG16 and VGG19 layers architectures. VGG16 contains 16 layers, and this one 19 layers. And why do we need to use small filters like 3x3 convolution? Stack of 3x3 convolution has the same effective receptive field as one 7x7 convolution layer. And can you calculate what is the effective receptive field of 3x3 convolution layers? Stop the video and think about it on your own, and let's check the answer later. Okay, let's check the answer together. For convolution, for single convolution, the receptive field will be 3x3. It's straightforward. What about the next convolution? I mean, when we stack 2 convolution layers, then this convolution covers this area, and this pixel covers this area. Therefore, in total, this single pixel depends on this area. Okay? And what about the next convolution? This pixel depends on these 9 pixels. And this pixel depends on these 9 pixels. And in total, this area. Therefore, this single pixel depends on these pixels. 1, 2, 3, 4, 5, 6, 7. It has 7x7 receptive field. And by stacking 3x3 convolution layers, we can achieve 7x7 receptive field. Okay. However, is it better to use 3x3 convolution than single 7x7 convolution? Yes, because by stacking more convolution layers, we can make our architecture much deeper, meaning that we are employing more nonlinearities. And by employing more nonlinearities, the representation power improves. And another advantage of using multiple smaller convolution filters than small number of large filters is we can use fewer parameters. For three 3x3 convolutions, we need to use 3 times 3 squared c squared number of field parameters. However, in the case of 7x7 filter, we need to use 7 squared c squared parameters for C channels. Therefore, we can make the representation power bigger, stronger, by using smaller number of parameters. That's the idea behind VGGNet. Okay, and this is how the input changes over these layers. And as you can see, the total memory is around 96 megabytes. And it uses total number of 138 million parameters. And we do not count biases here. And one thing to note here is most memory is in early convolution. And most parameters are in late fully connected layers. Because we are using 4096 times 4096 connections, like we need to connect all the components from this input. We need to use quite a large number of parameters for fully connected layer. And in the memory view, the first convolution layers need to use a lot of memory because the same weight, same convolution filter travels over the big size of the input. It travels all the way through the input, and it should store all this history, traversal, to calculate the gradient. So that's why this architecture uses most memory in the early convolution and most parameters in the late fully connected layers. Okay, and the naming convention is like this. These two are not named as convolution 1 or convolution 2, but convolution 1-1, convolution 1-2, like this. And the last three fully connected layers are named as FC6, 7, and 8. Okay, so the detail is it won the second in classification and first in localization. And it followed the similar training procedure as the AlexNet. And it did not use local response normalization, LRN, as in AlexNet. And VGG19 was bigger than VGG16. However, the performance gain was quite marginal, slightly better. So you can choose any of this. And also used ensembles for best results. And FC7 features generalize well to other tasks as well. Okay, so in 2014, deeper networks started to come out. And another network is Google Net, sometimes called Inception Net. It won the classification task, and it contained 22 layers. However, it only contains 5 million parameters, 12 times less than AlexNet, and 27 times less than VGG16. And it designed very efficient inception module. And by using this efficient inception module, this Google Net didn't need to use fully connected layers. And in the previous slide, I mentioned that most parameters are in late fully connected layers. But by avoiding fully connected layers, this architecture successfully reduced the number of parameters dramatically. Okay, let's have a look at what this inception module looks like. It designed a good local network topology, network within a network, and then simply stack this inception module to design GoogleNet. That is the basic idea. And naive inception module would look like this. This applies parallel filter operations on the input from previous layer. And we have multiple receptive field sized convolutions like this. And after each operation, concatenate all filter outputs together in the channel dimension. And what is the problem with this? Think about the computational complexity. Okay. And what would be the result of this naive inception module when the input size is like this? Stop the video and think about it on your own. Okay, let's calculate the output size together. After one-by-one convolution, it only changes the channel. So 256 becomes 128. And after 3x3 convolution, let's assume that there is a padding. Because we need to combine all these outputs together in the channel dimension, they should have the same spatial dimension, same width and height. And it changes the number of channels like this. And after the concatenation, size becomes like this. So the original size, 28 by 28 by 256, becomes this times 672. This naive inception module makes the input bigger and bigger, meaning that if we stack more and more inception modules, the input becomes huge, gigantic. And the convolution operation requires 854 million operations. That's too costly, very expensive. Okay, and to resolve this issue, the authors designed a bottleneck layers that use one-by-one convolution to reduce filter channel size. So we remember what one-by-one convolution is. We can reduce the number of channels using one-by-one convolution. Alternatively, we can interpret it as applying the same fully connected layer on each input pixel. And the difference between fully connected layer and one-by-one convolution is fully connected layers are connected to all the components or all the input elements. However, one-by-one convolution shares the weight and moves this weight over and over and calculates new value. However, for fully connected layer, to calculate this component, it has to refer to all the components, elements from the input. That is the difference. It preserves spatial dimensions, however, it reduces depth. Okay, so inception module with dimension reduction looks like this. Here we have one-by-one convolution to reduce the number of channels. So these are called bottleneck layers. And by employing these one-by-one convolutions, the total number of operations gets reduced from 854 millions to 358 millions, and the number of parameters as well. So that is the idea behind inception module. And using this inception module, they just stacked. However, the stem network, the first part of the network, looks similar to that of VGGNet or AlexNet. After processing the input image to some degree, to some extent, it goes through a stack of inception modules. Okay, this is stacked inception modules. And the classifier output, it involves fully connected layer to convert the input feature map W by H by channel into 1000 class cores. And after the last convolution layer, this one employs something called average global pooling. And average global pooling reduces all these spatial dimension into one by one. Therefore, even though this image, this feature map varies the size, like 256 by 256 by C, or 1024 by 1024 by C, it doesn't matter. They all becomes 1 by C. Which means InceptionNet can handle any sized input image. The previous network architectures cannot handle different varying image sizes. The input image size should be fixed to 224 by 224. However, because this one employs global average pooling, the input image size doesn't matter any longer. And they all also employed auxiliary classification outputs here and here, because this one is quite deep, and the gradient, after calculating loss from here, might not flow well. So in the middle, they calculated loss, and this classification module is the same one as the last one, and they calculate loss here. And these two additional losses help the gradient flow. And in the test time, we just delete these parts and only use this deeper network. Okay, don't use these two parts, or use this part. All right, so the idea behind GoogleNet is using deeper network with computationally efficient. So 22 layers, efficient inception module. What does it mean by efficient? It avoids expensive FC layers. And another big event happened in 2015 in Computer Vision Society. This is called Revolution of Depth. Before 2015, the deepest network was like 22 layers. However, after 2015, the network depth becomes like 152. And another thing is the performance of CNNs surpassed that of human. So after 2015, the performance was better than humans. Okay, let's talk about how ResNet became so deep. It used something called residual connection. And it could stack 152 layers, and it won 2015 image classification, and it swept all classification and detection competitions in ImageNet and COCO datasets. So this is simple description of what residual block looks like. And what happens when we continue stacking deeper layers on a plain convolutional neural network? And this is what it looks like. Even though we stack more layers, test error increases than 20 layers. However, this is nothing related to overfitting because the training error is also larger for 56 layered network. And why does it happen? The hypothesis is even though deep models have more representative power than shallower models, the problem is the optimization. Deeper models are harder to optimize. And what should the deeper model learn to be at least as good as the shallow model? A solution by construction is copying the learned layers from the shallower model and setting additional layers to identity mapping. So what does it mean? To use network layers to fit a residual mapping instead of directly trying to fit a desired underlying mapping. What it does is, basically, this will need to transform this X into something totally different using these two convolutions. However, using this identity connection, what these two networks need to learn is only the difference between the input and the output. Therefore, the burden for these two layers reduces because it only needs to learn the differences between the input and the output. However, it should transform the input itself to a different one. So the burden is quite large here. And another benefit of identity mapping is it gives another path for gradient flow. Therefore, the gradient can flow deeper and much better. Okay, so we use layers to fit residual connections instead of learning HX directly. And full ResNet architecture looks like this. It stacks residual blocks, and every residual block has two 3x3 convolution layers. And periodically, double the number of filters. So here we have 64 filters. However, 128 filters and 512 filters. And downsample spatially. And let's say the input size was 552 by 512. Then after this layer, the input size becomes 200 by 200 like this, and 64 by 64 like this. So both the spatial dimension decreases, however, the number of channels increases. An additional convolution layer at the beginning, and that is called sometimes stem layer. This one is similar to that of DFNet. And no fully connected layer at the end, only FC 1000 to output classes. Therefore, similar to InceptionNet, ResNet, because we have global pooling here, ResNet can handle any size images. And ResNet is also scalable. There are different sizes like ResNet 18 and ResNet 34, 50, 101, 152. And depending on your application, you can choose any of these. If your application requires a lot of data, then you might go with bigger ones. However, your application does not require much data, then you might go with smaller one. So depending on your application, you can choose the right sized ResNet. And for deeper networks, it uses bottleneck layer to improve efficiency, similar to GoogleNet. I told you that there are different versions of ResNet. For ResNet 18 and 34, they do not use bottleneck architecture. However, for these three architectures, they use this bottleneck scheme. So for the input, it first reduces the number of filter channels and then perform 3x3 convolution, and then recover the number of channels. Right, like this. Okay, in training ResNet in practice, they employed batch normalization and Xavier initialization. And they no longer use dropout, because if you use batch normalization, you don't need to use dropout. And use bigger batch size. And able to train very deep network without degrading the performance. And swept first place in all ImageNet and COCO 2050 competitions. And better than human performance for the first time. And ResNet, to the best I know, to the best of my knowledge, the ResNet paper is the most cited paper. And you can search online how many times this paper was cited. And we can compare the complexities. So VGGNet is quite big, like this. And over time, the accuracy improves. However, the model size also increases. InceptionNet version 4 is the combination of ResNet and InceptionNet. And VGGNet contains most parameters and most operations. And GoogleNet is most efficient. However, the performance is not the best. And AlexNet, small computation, but still memory heavy, low accuracy, because it is the very first CNN architecture. ResNet, moderate efficiency, depending on the model, and highest accuracy at the time. So that is why ResNet was so popular. In 2016, they trained multiple networks, Ensemble, and there were many attempts to improve the performance of ResNet, like multi-scale ensemble of Inception ResNet, ResNet, wide ResNet models. And this one was not that popular. However, SENet was quite popular. This SE stands for squeeze and excitation network. It is a feature recalibration module. It can be applied to any networks. This feature gets shrinked like this. So originally it was C by H by W. However, by applying global pooling, it gets shrinked to C by 1 by 1. So here it is squeezed. You can apply the same principle to ResNet. And it goes through fully connected layer and another fully connected layer. And the dimension reduces like this. And after sigmoid activation, the values become between 0 and 1. And using this weighting, the features get scaled. This is called recalibration. And this module allows this model to adaptively reweight feature maps. And this one won the 2017 ImageNet. And after 2017, annual ImageNet competition was stopped. And now you can access to ImageNet competition through Kaggle. Nowadays, people are working on more challenging data sets and challenging tasks. So you can use this data set for initial research. However, after your research becomes mature, you might want to use different data sets. However, the research into CNN architectures is still flourishing. Like improving ResNets, wide residual networks, rather than using 3x3 convolution with F number of filters, it uses F times K number of filters, making it wider. And you can also divide these three computations into multiple submodules or subpaths. This is called ResNext. And you can connect more, you can create more connections, and that is called DenseNet. And DenseNet is shallower, however, can outperform deeper ResNet. Sometimes DenseNet might be better than ResNet. However, it depends on your application. And after CNNs achieved the performance in human, researchers started to focus on the efficiency. And in 2017, efficient networks started to come out. And the first one was MobileNets. It reduces the number of parameters dramatically, and you can run these architectures on your smartphone. Nowadays, you can run CNNs or RNNs or other deep neural networks on your smartphones, thanks to these efficient networks. And this NAS, Neural Architecture Search, is to design the architecture through reinforcement learning. So rather than designing the architecture manually, why don't we just use reinforcement learning to search for the best architecture? However, generally, NAS research requires very large number of GPUs. Therefore, universities do not work on NAS that common. However, companies like Facebook or Google work on NAS quite a lot. So you can apply NAS or ENAS to find better architecture. However, sometimes smart heuristics is better than NAS. And EfficientNet was a seminal work. It designed very efficient network without using reinforcement learning. And as you can see here from this figure, the efficiency is better than other networks. However, the accuracy is higher, like this. And people are trying to move this plot to this area. And people generally use ResNet, MobileNet, and EfficientNet. These are the baselines for any research. And starting from these networks, people add more modules or modify the architecture of these architectures. Okay, this is the figure of where EfficientNet is. Okay, in this video, we talked about various architectures. AlexNet, starting from the AlexNet, VGNet came out. And this one used the stem block, and this stem block came out from AlexNet. And GoogleNet used Inception module or bottleneck connections for efficiency. And ResNet got the idea from AlexNet for stem network and bottleneck for bigger network architectures. And there are variants of ResNet and different architectures for efficiency or better performance, like EfficientNet as well. The main takeaways are like this. AlexNet demonstrated that you can use CNNs to train computer vision models. And ZFNet and VGG showed that bigger networks are better. And GoogleNet or InceptionNet is one of the first to focus on efficiency using one-by-one bottleneck. And ResNet showed us how to train extremely deep network. And this was the first network that was better than human performance. And after ResNet, CNNs were better than the human metric, and researchers started to focus on designing efficient networks. And trying to do so, they came up with the idea of neural architecture search, and some heuristics might be better in some cases, as shown in EfficientNet research. Okay, this is the summary. Nowadays, you can use many popular architectures on the fly. Many deep learning frameworks like PyTorch or TensorFlow offers the implementation of these architectures in their model zoos. So you don't have to implement these architectures on your own. You can just call some functions to implement those architectures. Okay, let's implement some of those architectures in the next video.